Hello everyone, this video is an introduction to quantum physics, and today we're going to talk about what is quantum physics and also some of the ideas and discoveries that led to this new field in physics. Let's start understanding a little bit better what is quantum physics. Well, the word quantum is a Latin-derived word that means quantity. And in physics, that's the smallest possible unit of a given quantity or quantifiable phenomena. If you think about a jar pouring water, okay, you can look at it in the microscopic level and see that this is a continuous phenomena, right? You can see water coming right here from the top and reaching the floor or the table, whatever, in a continuous form. But if you start to zoom in this stream of water, you would see the particles of H2O. So you would see that this water is not continuous anymore, but it's divided in small particles, okay? So physics, the quantum physics, is related to this really microscopic level, where the things appear not to be continuous anymore, but divided into small chunks. We're going to see later, but even the light that we study as a wave, it's actually quantized. So if we start to zoom in into a wave of light or a ray of light, we would see that actually the light is quantized. It has small particles that it's called photons, okay? And these particles here at this level, this really microscopic level, the particles and the things behave in a very strange and different way. So the classic physics does not apply anymore to this quantum level. Important discovery in quantum physics was the Balmer series. Balmer was studying the energy levels of electrons in an atom, and he realized that every time an electron goes from a higher level of energy to a lower one, it would emit an electromagnetic wave with a certain wavelength, and he could establish a relationship for the wavelength related to the level of energy of the electron. So N here is the level of energy. It starts in 3 because from 2 to 1 we cannot actually perceive the radiation that's emitted because it's outside the visible spectrum. But for all the others levels of energy, we could see the color of the radiation emitted. So this A over here is the symbol for angstroms, okay? Angstrom is 10 to the negative 10 meters, so it's really small wavelengths we're talking about here. And well, with his experiments, he could show that when the electron jumped from the third level to the second level, it would emit a electromagnetic wave with this wavelength here, 656.3 nanometers, and this represents the red in the visible spectrum. Then from the fourth to the second one, it would emit a turquoise light. From the fifth to the second, a purple light, and from the sixth to the second, a violet light. So see now that the lights emitted was not in a continuous form, but actually the spectrum was quantized. We cannot see colors in between these levels of energy. We would see some levels of red, and then it would jump to another level. The electron is just jumping from levels of state. It does not move continuously from one level to another, but it jumps. Another important idea, maybe the most important one when we talk about quantum physics, was proposed by Planck when he was studying black bodies. Black bodies in physics are certain types of bodies that can emit radiation all over the spectrum. We don't have perfect black bodies, but the sun is one that's really close to one because it can emit radiation not only in the visible range, but also the ultraviolet and infrared. But you can also think in a metal bar, that when we start to hit the metal bar, it starts to change its color because of the radiation it's emitted. Okay, so we can see that the radiation, the emitted radiation, is closely related to the temperature of the body. And Planck was studying it, and the thing is about these black bodies is that in classical physics we would predict that these lines here of the intensity of radiation would increase infinitely because we are decreasing the wavelength, we're making the waves shorter, okay, and consequently the radiation would be more intense and it will go to infinite over here. But studying the black bodies, they would see that the radiation would actually start to decrease at a certain point, and the classic physics would not predict this. So Planck started to make a relationship between the energy and the particles that were moving into this metal bar, for example. So he associated the level of agitation to a certain frequency, and then it would have a wavelength. So he was associating waves with these particles in this metal bar, and it would be able to predict this behavior here at a certain level. It would start to decrease the radiation. Then he came up with this formula that's now known as the Planck's law. It's simply saying that the energy emitted is an integer number times the Planck's constant h times the frequency of radiation. So see now that he is associating what was known as a continuous thing, like energy, to the frequency of radiation. But the thing here is this integer number here. It says that we don't have a continuous change in energy, but we jump from levels of energy that's associated to the Planck's constant. So if we start to zoom in into this violet part of the spectrum, at a certain point we wouldn't see a continuous color anymore, but chunks of violet or chunks of energy. So he was saying now that the energy was not continuous at a certain point, but it was also quantized. And this was one of the most revolutionizing ideas in physics that made people start to think about this quantum physics and these really microscope levels. See, that's really small. We're talking about this constant here is a number times 10 to the negative 34 joules per second. So it's really tiny. It's a quantum level. So at this point here, we could not divide energy anymore, and we would see it in chunks. And that's the basis for the quantum physics we know nowadays. So that's it. Hope you liked, and see you next time.
Physics can be easy. Subscribe to our channel and learn with the geeks.